Second order LC response. To date we've looked at first order systems, either RC or RL circuits, both driven by an independent voltage source, or we could equivalently drive them with an independent current source. We found that in both cases we ended up with a differential equation of the form some time constant tau, the derivative of the voltage for the capacitor circuit, plus the voltage is equal to Vs. And for the RL circuit we found dIL dt times tau plus IL was equal to, turn out to be Vs over R. But it's a constant. We can replace this with some Is equivalent. We found that the solution for that, for both these equations, was of the form e to the st, e to the st, where s is some constant. So we found, first we looked for the particular solution. We found that the total solution was equal to a particular plus a homogeneous. So going after the particular solution, we assumed that the particular solution was some constant. And we plugged that in, and so we got tau times the derivative of a constant plus a constant was equal to a constant. Of course, this is 0, so we found that k must be equal to Vs. Therefore, the particular solution was Vs. We can do the same thing over here, and we find that the particular current was equal to Is, where Is is Vs over R. We then went, put particular here, particular solution. We then went for the homogeneous solution. And remember, this is due to the initial energy in the system, whereas the particular solution is due to the external forcing, in this case Vs over Is, which really is Vs over R. So for the homogeneous solution, we return to our differential equation and we set the right side to 0. And we did that for both cases. And again, we looked for, well, what solution for the capacitor voltage would possibly result in satisfying this equality. In particular, the function for the capacitor voltage, when added to its derivative scaled, must equal 0. So a good candidate is the exponential. So we try V, C homogeneous, is equal to some A e to the st. We plug that in, and when we take the derivative, we get s out in front. We get A e to the st back again, plus A e to the st is equal to 0. We pull out the A e to the st, and except for the trivial case where A's would be equal to 0, the only other way that this equality is satisfied for all time is if tau s times s plus 1 is equal to 0. In other words, s is equal to minus 1 over tau. And therefore, we could write Vc homogeneous is A e to the minus t over tau, where tau we had found, well, I didn't write it up here, but in writing the differential equation back up at the top here, we would find that tau would be equal to Rc, and for the RL circuit, tau is equal to L over R. That comes about very straightforwardly if you write, here let's just do, for this one, let's do KCL. At this node here, we would say the current leaving to the capacitor is IC plus the current leaving through R, which is going to be VC minus VS over R is equal to 0. We replace IC with C dV C dt, and then we multiply through by R, so we get RC dV C dt plus VC is equal to VS. And we see here this is tau. We can do the same thing for the RL circuit, and we find that tau is L over R. So back to our circuit down here, we find that the tau is equal to RC. So now we combine the particular and homogeneous solutions, and we find the total solution. So VC of t is equal to the particular solution Vs plus A times e to the minus t over tau. And we have yet to find what A is. So to do that, we satisfy initial conditions. Alright, and that is VC at time 0 is equal to some initial voltage. We'll just call it V naught. So let's go back up here and specify this is where VC of 0 is equal to some V naught, and IL at time 0 is equal to some I naught. Could be 0, could be a non-zero value. So we need to make sure that this function here, when evaluated at time 0, evaluates to V naught. So let's go ahead and set it equal to it and pick our A such that that is the case. This goes to 1 at time 0, and so we find that A must be equal to V naught minus Vs. Therefore, the complete solution is Vc of t is equal to Vs, the particular solution, plus V naught minus Vs times e to the minus t over tau. And this is for all time greater than or equal to 0. And we'll say that tau is equal to Rc. All right, and we can do the same thing for the current. If we go down, we'll find that the complete solution is IL of t is equal to Is, which is in this case Vs over R, plus our initial current I0, Ri naught, minus Is e to the minus t over tau for time greater or equal to 0, and where tau is equal to L over R. So for instance, if Vc of 0 is equal to 10 and Vs is equal to 5 volts and R times C is equal to 1 millisecond, right, then if we plot this Vc versus time, it would start off at 10 volts. Here's 5. And I'll start the time here at 0. At time 0, it would exponentially go down and asymptotically approach 5 volts. And the time constant would be, basically the solution would be 5 plus 5 minus 10. 5 plus 10 minus 5 times e to the minus t over 1 millisecond. And that's what it would look like. Okay. That's enough on the first order review, and now we're going to go through the same process, but for a second order system. Alright, so let's draw our second order system. We have an inductor, we have a capacitor. We'll leave out a resistor for now and come back and add that in the next step. But we'll first solve this problem. So let's first write the equations of motion. The equations of motion. This is what we always do. I skipped it last time for the first order and just gave the differential equation, but here we're going to go through it and we'll arrive at a differential equation once again. So let's do KVL. You could do it either way, but let's do KVL around the loop. Okay, and so we'll have minus Vs plus, all right, because of the current direction here, current's going in, this is the plus to minus VL, all right, plus VL of t plus VC of t is equal to 0. VL for an inductor is equal to L dIL dt, okay, and let's say that I want to solve this I want to express the equation of motion in terms of Vc. So I'm going to leave Vc here, and I want to express this first term ultimately in terms of Vc. So I've got it in terms of IL, but I also note that this is equal to L dic dt, right? Because it's the same current, right? And then I can say that remember IC is equal to C dVc dt, right? Just like VL is equal to L dIL dt. So I can replace IC, and I'll have LC d, and it's going to turn into the second derivative now, d dt times dVc dt, right? So we'll have LC, second derivative of the voltage, with respect to time. So therefore, let me write our final differential equation. We have LC dVc, second derivative, with respect to time of the capacitor, voltage, plus Vc is equal to Vs. This is our second order differential equation. Once again, we want to try to find the particular and then the homogeneous solution. So, particular solution. We're going to try the approach we had before, which is essentially, if we see the system being forced by some constant, which is the case here, we're going to assume that the particular solution will also have that same form. So let's just try Vc particular equal to just some constant. All right, try it. So we get LC times the second derivative with respect to time of k plus k is equal to Vs. This, of course, is 0, and we find k is equal to Vs, which therefore Vc particular is equal to Vs, just like before. So that did not change from the first order system. Third, let's find the homogeneous solution. Once again, we see that what we need here is a function for Vc such that its second derivative with respect to time, scaled, plus the function itself has to equal 0. And let me write this out. I forgot to write the homogeneous. Remember, we turn off the external sources. Homogeneous form, right? We turn this off, the external forcing. So we're going to try our handy exponential again. Try VCH t is equal to some a e to the st. We'll plug that in. We have LC times, and now when you take the second derivative of that function with respect to time, you're going to get s comes out, and then the s is going to come out a second time. So we'll get s squared a e to the st plus a e to the st is equal to 0. Collect terms, and this is looking very much like what we had for the first order system. So, except for the trivial case where we would have a equal to 0, which would be useless, we are going to satisfy this equality by ensuring that s squared is equal to minus 1 over LC. which means that s is equal to plus or minus the square root of minus 1 over LC. Or we could say plus or minus square root of minus 1 over square root of LC. And now we have something strange here. We have the square root of a negative number. So we are going to have to deal with imaginary numbers. Alright, if you are not comfortable with complex numbers, I would encourage you to pause at this point and look at some review on complex numbers and then return, because I'm not going to cover it in this lecture here. I will just assume your knowledge of it. In math classes, usually you would represent the square root of minus 1 by the letter I, but because we're in electronics or electrical circuits, we use, this in math or physics, here we will use the letter J, alright, in engineering, just so we don't confuse, so as not to confuse with current. Okay, so we have therefore our solution is S is equal to plus or minus J times 1 over the square root of LC. Now we're going to define we're going to give this 1 over square root of LC a name. We're going to say that it is a frequency omega n. This will become apparent eventually, but we will define this omega n as being 1 over the square root of LC. Therefore, S is plus or minus J times omega n. Okay, where omega n is equal to 1 over square root of LC. So let's return to our homogeneous solution and see what happens here. So we have VC of H is equal to, and here we have to think about what this means. We have more than one value of S for which e to the st, or a times e to the st, will actually satisfy the homogeneous solution. So we could say the solution is a e to the plus j omega nt. Alright, this is S here. I'll call it S1. That's a solution. But we also have that some other, I'll call it B instead of A, just another constant, B e to the minus j omega nt, where minus j omega n is S2, or second root. That is also a solution to our homogeneous solution. And so if I plug one in and it evaluates to 0, thereby satisfying the homogeneous differential equation, and I plug in the second one and it evaluates to 0, thereby satisfying the homogeneous solution, then the most general solution would be one that would include both of these individual solutions. And what I do is we put these constants, A and B, in front, so that when it comes time to satisfying the initial conditions in the final step, the initial conditions will ultimately determine whether both these solutions, both these terms are involved or not. And if one of them isn't, then A will drop out, or A will be 0, or B will be 0, as the case may be. It turns out in this case they usually are all they're working together, and we'll see that play out here shortly. So we can sit here and look at, ask ourselves how do we proceed at satisfying the initial conditions. What's weird is, or strange, is that we don't know maybe what to do with this exponential function, a complex exponential function. So we need to do a little bit more, math review. Actually, let's hold off on doing some math review. Let's try to take this a little bit further by actually plugging this homogeneous solution in, or combining it with the particular solution and solving for initial conditions. And let's see where we get with this solution. And then when we get stuck, we'll go back and do some math review. So we're going to combine now. So here we have our homogeneous solution. It looks strange. We don't recognize real signals that look like this, but we'll just see what happens as we go forward. Alright, so complete solution. So the complete solution, VC of t, is equal to the particular solution plus the homogeneous solution, which will be Vs plus a e to the j omega nt plus b e to the minus j omega nt. Now we need some initial conditions. I hadn't set them previously, but let's say that we have, in this case, let's assume, so for IC's initial conditions, assume the following. Now in the first order circuits, we had one initial condition. So if we had a capacitor in the circuit, there was an initial capacitor voltage. If there was an inductor in the circuit, there was an initial inductor current. Now that we have both inductor and a capacitor, we need to specify two initial conditions. This is just like if you had a mass spring problem, like you're going to, a mass hanging on a spring and you're going to excite it or do something with it. You would have two initial conditions. The position of the spring, like is the spring at rest, is it compressed, is it stretched, and then the initial velocity on the mass. So we have the same thing here. Let's assume this is going to be the simplest case. We'll assume that the initial condition on the capacitor voltage is 0, and the initial current through the inductor is also 0. Alright, so this is a special case, but we'll go ahead and start with this. So let's plug in. Vc at time 0 is going to be equal to 0, but it is also equal to Vs plus a times e to the j omega n0 plus b e to the minus j omega n0. These go to 0, or go to 1, I'm sorry. And so we find that Vs plus a plus b must be equal to 0. So let's just hold on to that for now. We'll come back to it in a minute. Now we need to satisfy the second initial condition. How do we do that? This equation that we have is in terms of capacitor voltage, not inductor current. So we need to go back to our circuit. We need to look at our circuit. We have the capacitor voltage. This we know is this expression Vs plus a e to the da-da-da plus b e to the da-da-da. Okay? The inductor current IL is also the capacitor current IC, right? Note that the current IL is related to the capacitor voltage by C dVc dt. So, the initial condition IL of 0 is equal to 0 is really equivalent to restraining C dVc dt evaluated at 0 to being 0. Alright, because this is IL. So let's do that. C times the derivative of our time domain expression here for VC. Let me go ahead and write this back up here because I think we're going to need it. J omega nt. Yes. Okay. So C times the derivative of this whole expression, Vs plus a e to the j plus j omega nt plus b e to the minus j omega nt. Right, and that's equal to 0. So I might as well get rid of that c. It's not going to be useful. We take the derivative of Vs, that's 0. Take the derivative of the second term and we get plus j omega n a e to the j omega n t plus minus j omega n times b e to the minus j omega n t is equal to 0. And of course this is evaluated at t equal to 0. So that's convenient. This all reduces. This goes to 1, right, when we evaluate it at time equals 0. So we get j omega n a minus j omega n b is equal to 0, or a must be equal to b. So let's return to the constraint that we found from satisfying the initial capacitor voltage, and that was Vs plus A plus B is equal to 0. This right here is equal to 2A, or 2B. So therefore we can say that A is equal to minus 1/2 Vs. And it's also equal to B. Alright, so now we can write our complete solution. Here we go. Vc of t is equal to the particular solution, Vs, plus A, which is, I'm going to put this out in front here, A times e to the j omega nt plus e to the minus j omega nt. Okay, let me rearrange this a little bit. We'll say this is Vs times 1 minus 1/2 e to the j omega nt plus e to the minus j omega nt. Now here's where we have to do a little math. I won't cover this here, but I want you to, if you don't remember this or don't know this, look up Euler's formula. Okay, which says that e to the ix, or jx as we are using j for the imaginary number, e to the jx is equal to cosine x plus j sine x. Alright, or maybe it's better to say e to the j theta is equal to cosine theta plus j sine theta. If you think of a unit circle and you have a real axis and an imaginary axis, and if we have a vector along here, and this is a unit vector, and we have an angle theta, okay, this distance here is cosine theta, and the vertical distance here is sine theta. Now if we think of this as the complex plane, okay, then if I have some vector out to this point here, it has some x value and it has some y value. But the y value is on the imaginary axis, the x is on the real. So what I really have for this number here, call it z, okay, this complex number, I have z is equal to x plus jy. This is in Cartesian coordinates. Well, I can also represent that number in polar coordinates. Now this would be familiar, maybe more familiar if we're not talking about real and imaginary axes, but just maybe a two-dimensional axis, an x and a y. But that's essentially what's going on here. This is polar representation and this is the Cartesian representation for the same number. Okay, If you look at this, we can say something, like for instance, the magnitude. What is the magnitude or the absolute value of e to the j theta? Well, if you believe me that e to the j theta is this vector here, as represented clearly, if you look at Cartesian coordinates, it's got a real part cosine theta and an imaginary part sine theta, then the magnitude is simply equal to the square root of the real part, or the x part squared, plus the square root of the x part, the real part squared, plus the imaginary part squared. And we all know that the cosine theta squared plus sine squared is equal to 1. So the magnitude of this is equal to 1. All right, so how does that help us here? Well, we're going to take these two terms here, and we're going to replace them with these trigonometric forms. Although what I would rather do is I'd rather play a little trick here first and just say, let's consider the following. Instead of plugging that in, it's going to be messy. Let's do a little more work first. Consider the following. Okay, what if we have e to the j theta, I said was cosine theta, plus j sine theta? And what if I have e to the minus j theta? What would that be? Well, it would be cosine of minus theta, but cosine is an even function, so cosine of minus theta is the same thing as cosine of theta. And then it would be plus j sine of minus theta. Sine is an odd function, so the negative sign comes out, turning our plus out here to a minus. Now what if I added these together? Alright, so here I would have e to the j theta plus e to the minus j theta, and over here I get 2 cosine theta, and then the signs cross out. So I can write that 1/2 of e to the j theta plus e to the minus j theta is equal to cosine theta. Well, that's interesting. We can do the same thing and show, so I'll leave this for you to practice, that 1 over 2j times e to the j theta minus e to the minus j theta is equal to sine theta. Now, let's look at this expression up here. Is that not simply this expression? And so we can go plug this in here. So, we can therefore write, therefore, Vc of t is equal to Vs times 1 minus cosine of omega n times t. Wow, that is pretty amazing that we got through all that nasty math and ended up with something that looks pretty familiar. So let's now look at what that actually looks like if we were to plot it. Alright, so let's plot this versus time. Let's say this is Vs, and our capacitor voltage, remember, starts at 0. That was our initial condition. This is for Vc of 0 is equal to 0, and IL of 0 is equal to 0. Alright, and we have Vs. Now this starts out at time 0, cosine omega 0 is 1, right? So we get 1 minus 1. So we start down here. That's good. So we satisfy our initial condition. And then let's just replace all this with theta. I just rather plot this against theta because it's just easier to, right? So theta is equal to omega n times t, and if you're confused, this is 2 pi over the frequency. All right, so remember, let's just do this, recall that where did we get omega n? That was what we defined to be 1 over square root of LC. So notice that the frequency at which this cosine repeats itself is dependent on the L and C values. The smaller the values are, the faster, the higher the frequency. So we find that at pi, let's do this. Let's do pi over 2 pi 3 pi over 2 and 2 pi. Okay, so we start at 0, and at pi over 2 we are going to be at 1. Oops. Alright. And then at pi, cosine of pi is minus 1. So 1 minus minus 1 will take us up to 2 Vs. So that would be up here. And then at 3 pi, we're going to be back to 0. And we'll find that this oscillates. Right? And it just oscillates forever. It never dies down. But it has a particular solution. If it were to die down, it would die down ultimately at Vs, which we found to be our particular solution. It just so happens that in this case, because there is absolutely no resistance, we just have an ideal inductor and capacitor. That's like having an ideal mass in a spring. The mass, or there's no friction, there's no drag, nothing. It would just oscillate forever. Now let's go back and try solving this one more time with a different initial condition, just to show you how this can kind of evolve to be a different but yet similar form. So let's repeat, but with the initial conditions as follows. Vc of 0, let's say instead of being equal to 0, let's say it's Vs. And IL of 0 we'll say is equal to, we'll just say 1 amp. Okay? So we have to return to our complete solution, where we have the particular solution plus our A e to the j omega nt plus B e to the minus j omega nt. And now we're going to plug that in. We're going to plug in 0 for time and satisfy our initial condition for capacitor voltage. So we'll have Vs is equal to Vc of 0, which is equal to Vs plus A plus B. Remember, the exponents cancel out. In this case, these cancel, and we'll have that A is equal to minus B. Now we have to satisfy the initial current condition on the current, which is equal to 1 amp. So remember how we got that. That was equal to C dVc dt, evaluated at time equal to 0, which we found previously was, let's see, j omega, what's C, times j omega n A e to the j omega n times 0, right, minus j omega n b e to the minus j omega n 0, right? These go to 1. And so what do we have? We have 1 over C, 1 amp over C, is equal to j omega n times A minus B. Okay, and this, from our first condition, right, is equal to 2B. Right? So now we can solve, or it's 2A, whatever. What did I say it was? 2A, I mean, I'm sorry. 2A. So let's solve for A. So A is equal to 1 amp over 2c times omega n. This is confusing because this is variable A, this is amps. Okay. And let's actually let's go a little further here. Let's go 1/2. I'm going to drop no, I'll leave the amps in there. A. And then what do we have down here? We have, this is C, and then remember omega n was equal to 1 over square root of LC. Right? So let's put that in, and that'll put LC up here. So I have 1 amp times 1/2 square root of L over C, if I pull that other C in. Okay? So let's clean this up. We'll have VC of t is equal to Vs, alright, plus A, which is this 1 amp times 1/2 square root of L over C, times e to the j omega nt. But now, because I have B is equal to minus, or A is equal to minus B, I'm going to have a minus sign here. Alright? Minus e to the minus j omega nt. Now, if I go back to what I'd done with Euler's formula before, let's recall that that sine of theta was equal to 1 over 2j e to the j theta minus e to the minus j theta. And if you notice, we have exactly that here. We have this piece and we have the 1/2. Oh wait, I forgot my j here. Let me go back and put my j into all these expressions. That was a mistake. So I have j in all of these. So I see that actually here I have a sine term. So now I can replace this with the sine term. I have 1 amp times square root of L over C times the sine of omega nt. And let's see what that looks like. So here I've got Vs, got Vc, and time. At time 0, the sine function sine term evaluates to 0, so I actually start it at 0. Let me make a couple markings here. So pi over 2, pi, 3 pi over 2, 2 pi. Okay, so I will start at 0, and then it will rise, and I'll reach a peak here. Come down, and I'll continue. Okay, now let's think about this. Why would this response look different than the one up here? Well, this is for the condition where Vc at time 0 is equal to Vs, and IL at time 0 is equal to 1 amp. So let's go back and look at the circuit, what we have here. If I have at time 0 1 amp flowing, okay, and it's flowing into the positive terminal of the capacitor. And remember that the capacitor voltage, we can say that it's related to the current according to I equals C dV dt. Right? But we can also say Vc is equal to 1 over the capacitance, the integral of the capacitor current. Okay? So, if I start off with positive 1 amp flowing into the capacitor, then when I integrate positive 1 amp, that will result in an increase in the capacitor voltage. And it makes sense even without thinking about the VI relationship if we just simply remember that when you deposit charge onto the positive plate of the capacitor voltage increases. And that is what we see in this region here. Eventually what happens is at this peak here, okay, the voltage across the capacitor ends up being 2 Vs. And at that point, because we have Vs over on the left side, the voltage across the inductor at that point ends up being minus Vs. And what begins to happen at that point is there's a sufficient negative voltage across that inductor that it slows the current down. And the current now actually starts, well, it has been slowing down, it actually reverses and starts flowing negatively into the capacitor, thereby pulling charge away and sending the capacitor voltage back down again. When you get down to this point here where the capacitor voltage is 0, you now have a situation where you have Vs on the left and you have basically no voltage on the right, and so you have a positive Vs across the inductor, and that causes a positive increase in the current. Remember that for inductor current we write it as IL is equal to 1 over L integral of the voltage. And so if we have a positive voltage across the inductor, as you integrate that, that positive voltage will result in an increase in the voltage, and that is, or in the current, I should say. And as that current starts increasing, it will again deposit charge onto the capacitor, causing the capacitor voltage to go back up. Alright, so at this point, what have we accomplished? We have worked through, we've ground through the math to solve our first second-order differential equation, or second-order circuit. But we have constrained ourselves to an LC circuit. We have not yet looked at an RLC circuit. I think before introducing the R, I want to take one more look at the solution to this problem, and maybe save us some pain in the next go-around. You notice that although we solved both of these cases, the two initial conditions, by starting with the two e to the j omega nt and e to the minus j omega nt terms, and we plugged that into our, we added that to our complete solution, and we solved for the initial conditions. We found that in the end, once we satisfied initial conditions, these complex exponentials went away, right? They combined together in such a way to produce either a cosine term or a sine term. Now, in general, actually I chose the initial conditions such that we had purely a cosine and purely a sine term. But we could have a case where there's a combination of the two. But the thing that will always be true is that these complex exponentials will always combine in such a way to actually produce just real valued functions, either a sine or a cosine. So I want to propose something. Here's a proposal. Consider the form for VC of t as follows. So I'm going to go back to the complete solution, but I'm going to, instead of writing, well, here I'll write it one more time, then I'm going to get rid of it. Instead of writing Vs plus a e to the j omega nt plus b times minus j omega nt, we're going to cross that out, and we're going to use instead Vs plus b, let's say, c times cosine omega nt plus d sine omega nt. Now what I'm doing here is I made an observation from the work that we've done so far, and I concluded, you know what, for these real valued or real problems, the resulting voltage and current is always real valued. I mean, can you imagine somehow having an imaginary voltage or an imaginary current? I mean, that just doesn't make sense. No physical system has imaginary voltage or imaginary current. And certainly these two cases that we worked out, the complex exponentials did go away, combining so as to produce real valued sine and cosine values. So why don't we just try that right from the beginning? Let's not start out with the complex exponentials. Let's go straight to writing a cosine term and a sine term. Now let's plug it in, or let's try to satisfy the initial condition. So let's do both cases as before. So once again, try the initial conditions. Vc of 0 is equal to 0, and IL of 0 is equal to 0, and then we'll do the second one as well. Okay, so here we go. Vc of 0 is equal to Vs plus c times 1, right? Because cosine of 0 is 1, plus d times 0. this right away tells us that C is equal to minus Vs. Then we have to satisfy the condition that IL of 0 is equal to 0, and that we have found by saying C dVc dt at time 0 is equal to 0. So let's do that. Let's take the derivative of our expression above. We'll get 0 for the derivative of Vs. We'll get minus C times omega n sine omega nt, and we'll get plus d omega n cosine omega nt. We're going to plug in 0, time equals 0, so we'll have C times, oh, you know what, I shouldn't have used, this is C the capacitor. I see now that I'm double using C, so C the capacitor. We'll have, boy, I made a mess here. Okay, well, anyway, this goes to 0, so fortunately we don't need it. So we get 0 minus 0 plus d omega n is equal to 0. Therefore, we have d is equal to 0 as well. So we can now write our solution. Therefore, Vc of t is equal to Vs plus C, which is minus Vs, cosine omega nt plus 0. Or in other words, Vs is 1 minus cosine omega nt. Lo and behold, this is exactly what we found previously. So that's good. That's great. Now let's try the second initial condition set. Okay, and that was Vc of 0 is equal to Vs, and IL of 0 was equal to 1 amp. So let's plug it in. Vc of 0 is equal to Vs, is Vs, which is going to be equal to Vs plus, you know what, I'm not going to use C for my, I'll go ahead and I'll make it a funny C. C times cosine of 0 plus d sine of 0. So this crosses out, and I find Vs equal to Vs plus C, so therefore C is equal to 0. Then IL at time 0 is equal to 1 amp. That's equal to my capacitor times the derivative of Vc of t. So that's C times, let's do that again, it's going to be 0 minus C. You know what, I don't even need to take the second term because I already know that my scalar in front of the cosine is 0, so we're going to ignore that. We'll say plus d omega n cosine omega n times t, evaluate at time 0. So here we have 1 amp is equal to C, the capacitance, times d, the constant, omega n. And we can solve for d, which will be equal to 1 amp times 1 over omega nc, which we solved before, that's equal to the square root of L over C. So therefore, and we can write it out, Vc of t is equal to Vs plus d sine omega nt. So that's 1 amp times square root of L over C times sine omega nt. And that is the same answer that we found earlier. And so therefore, we can use a trig solution form instead of a complex exponential form, which is a good news. All right, I want to do one more thing. All right, one more form for Vc of t. All right, since we're on a roll here anyway, we tried Vc of t was equal to, this is for the complete solution. We wrote Vs plus a e to the j omega nt plus b e to the minus j omega nt. We then tried Vc of t is equal to Vs plus c cosine omega nt plus d sine omega nt, and that worked. And now I want to try one last form. What if we did this? Vs plus, I'll say k, times cosine of omega nt plus theta. All right. Or we could also try L sine omega nt plus v. Okay. But we won't do both of those. Let's just try this first one. All right. So if we have the initial conditions of VC of 0 is equal to 0 and IL of 0 is equal to 0, then let's plug this times 0 in and see what we get. We get Vs plus K cosine of 0 plus theta is equal to 0. All right, so therefore we get K is equal to Vs over cosine theta. All right, then let's try IL of times 0 is equal to 0, which is equal to C times the derivative of all this, so we'll get derivative of Vs is 0, plus the derivative of K cosine omega n is going to be minus omega n K sine omega n t plus theta. And that is evaluated at time equals 0. And so we'll find that we have sine of theta must be equal to 0. Let's choose theta be equal to 0. So therefore we have K is equal to Vs over cosine of 0, which is equal to Vs. And we can write our solution. Vc of t is equal to Vs plus K, which is Vs, times cosine omega nt plus 0. And this is exactly what we found the previous two times. You could repeat this as well for the second initial condition case, and you would find that it would evaluate to, so let's just say, try IC of VC of 0 is equal to Vs, and IL of 0 is equal to 1 amp. You will find that Vc of t will be found to be Vs plus Vs sine of omega n t, I'm sorry, cosine of omega nt minus pi over 2, right? Because cosine theta minus pi over 2 is the same thing as sine. All right, we'll stop here, and next time we will return to our original LC circuit, but then introduce a resistance.